All right, everyone. Thank you so much for looking at this video. Here we are going to discuss the main objective of this module that uses, again, quoFEM, but now in the context or with the objective to do uncertainty quantification on pushover curves of buildings. So this module has three main learning objectives. We want to introduce the concept of nonlinear static analysis or pushover, describe the general computational workflow to produce or to make a nonlinear static analysis using OpenC's, now using the Tickle interpretation as opposed to the OpenC's Pi interpretation that we have already used in a couple other modules here. And then finally, quantify uncertainty in that pushover curve or that nonlinear responsive structures to consider that and to factor in uncertainty into our decisions, and finally the recommendations we can provide a stakeholder or a decision maker that wants to understand their performance, specifically focused on, for example, earthquakes for their building, and that will be the context that we will be thinking about this. So let's start by kind of revisiting the concept of nonlinear static analysis. So starting with a conventional seismic design, any structural engineer is familiar with the typical approach for designing structures to resist earthquakes, right? The traditional sort of approach or building code approach for new buildings relies on linear analysis of a structural system, but then uses a simplified design best shear approach when the concept is that we will kind of estimate the period of the building, get the lateral forces based on a design spectrum that kind of reflects the hazard, the ground motion hazard at the site, get those loads, and then artificially reduce those loads with an R factor that would kind of take care of or consider some of the nonlinear aspects, and we'll revisit that in the next couple of slides. All of these sort of design approach kind of heavily relies on prescriptive rules and that have been carefully calibrated over the years with the design and the learning, the design of multiple buildings and the learnings we have gained as a profession from multiple earthquakes that have happened in the past. Of course, the outcome of the response is still uncertain because we are kind of treating the problem deterministically and have some kind of levels that to introduce a factor of safety with the load and resistant factors and all that kind of design approach, and that theoretically we should give us the level of confidence that we want to achieve the performance, the structural performance that the code looks for. And I think that's a really good point that we need to highlight, and is that owners, the decision makers that the structural engineers offer their service to, are normally informed of complying with the building code, but are not always aware of what that means in terms of the performance of the building they are getting. And to be clear, what the current building design codes promise is life safety, right? Which in other words means that when the design earthquake happens, then the building would be expected to be severely damaged, have a really high likelihood of required demolition, right? So all of the patrimony, all of the investment would be lost, but the building would theoretically provide enough time for occupants to evacuate and would therefore save lives, right? That's the concept. So all of the performance that building codes for seismic design are built upon is on saving lives, not saving patrimony. So damages during the design earthquake would be really high and potentially demolition is required. Now let's go back to this concept of the R factor, right? This R factor is basically tabulated in the building codes depending on the structural system. In some codes in other countries, it also considers the period of the structure and other characteristics. And basically is a way to simplify the design and to encapsulate many complex factors and many complex processes that are happening when the structure goes in the nonlinear range of response, right? It considers the ductility, which is the ability of a member to deform beyond the elastic limits and maintain the load carried capacity. So basically not break at all completely, but sustain that force despite that it cannot get more, and dissipate energy, the overstrength of the materials and the over designs that can happen, the redundancy in the system, right? And when if you need to collapse a building, there is many elements depending on how redundant the structural system is that need to break before the whole system collapses. Also tries to capture the effect of damping of non-structural components, you know, walls and partition walls and all of those members that are inside the building that we typically ignore in structural analysis, and some other phenomena there that really affect the nonlinear response of the structure. And the concept is that at least the building codes predicate is that they want a cost-effective structure, right? A structure that would be safe enough for a fair amount of initial investment, right? Because we have the tools to make buildings just withstand any earthquake elastically, right? And barely suffer any damage. The trouble is that they will require, right, a lot of material, a lot of steel, concrete, really huge elements that would, you know, would cost a lot of money and would place limitations architecturally and all that. So these are factors of that compromise when we will allow some nonlinear response, which basically means we will allow damage in the building, just to such that the cost of construction is lower, and then we still keep that life safety performance objective. However, this performance objective, the life safety performance objective is not always acceptable for a building owner, and that's something that with advanced analysis, nonlinear structural analysis, starting with a pushover analysis, we would be kind of able to go beyond the code and do designs and do analysis and retrofit of existing buildings and risk assessment of buildings that will kind of estimate and consider the response of the building as it is without kind of resorting to these R factors to estimate potential good performances, but instead quantify the response as it is. And so the concept of the pushover really focuses on or starts with the assumption that we will have a mathematical representation of the building, of the structural system, and we will apply lateral forces to that building that would be equivalent to the effect of the ground motion, right? So basically, kind of the most typical is the equivalent lateral force type of method that's on the code. We could estimate what are the forces in each floor and then apply those forces to the building. But the difference is that our model can capture nonlinearity, right? So it would break, it will start yielding, and have the effects of nonlinear response in all of the elements that are included in the mathematical model. And the concept is that you take that lateral force and you start increasing it monotonically until the building starts damaging, and then then you can kind of plot this so-called pushover curve when in the horizontal axis you have the deformation at a point in the building, typically the roof. You track sort of the displacement of the roof and start kind of tallying up what's the base shear. That it's basically the summation of all the lateral forces that you are imposing, right? So you're pushing the building laterally following a fixed load pattern, right? And that load pattern will be kind of producing damages until at one point you get enough elements damage that will form a mechanism, and then you start collapsing the building, right? This could also in the realm of performance-based earthquake engineering, this figure has been used a lot to also show the different performance levels of the building, right? You can have a building that has minimal damage here, continue very functional, a building that has moderate damage, relatively functional, and then a building that has severe damage but hasn't collapsed, so it complies with the life safety target of the building codes, where yes, you have a lot of damage, but you have time to evacuate, and then an unacceptable response, which would be basically total collapse with high risk of losing lives. However, doing this type of advanced models and nonlinear analysis of structures for a pushover, for example, it presents a complicated situation for the structural engineer, because those models are a lot more complex than the typical linear models that one would do for designing a building following the building code, right? For example, here is Really simple, perhaps the simplest structure that you can think about is a portal frame, 1 bay, 1 story. And if you want to do a concentrated plasticity model of this type of structure using just 1 type of beam, 1 type of column, you will have 3 types of nonlinear springs. You have the hinge of the column, the hinge on the beam, and the hinge of the panel zone. Each of those have at least 6 parameters, which means that this very simple structure has 18 parameters at the very least. If you start considering, you know, cyclic degradation and all of those things, pinching behavior, then you have a lot more than 18 parameters for this very simple the structure. So how do you, you know, how are you certain that the values you assign to each of those parameters really reflect the real building that will be constructed or that is constructed in the case you're trying to estimate the response of an existing building, right? It is really a lot of uncertainty there, and the more parameters, the higher the uncertainty, that because you have less and less information to calibrate those parameters properly. So it's really important to kind of acknowledge that uncertainty and what that means in terms of the pushover, right? So for example, here we're looking at the same kind of conceptual pushover curve, but because of all of that uncertainty of we really not having enough information to calibrate all of those parameters that go into nonlinear models, what that means is that the pushover curve that, you know, using nominal values could be this thick red one, could also be this lower one or this higher one. And in practical terms, what that is saying is that if you target a deformation level, for example, a drift limit based on the building code, you can have multiple performances depending on what are the exact parameters of the real building, right? So if you say this is the 2% drift or maximum drift from the code, and then you say, well, for that, with my nominal properties, I get life safety performance, so I'm good, I'm fulfilling the code. But then what happens if, because of all of this uncertainty that, you know, it's embedded from material properties, from construction practices, from the environmental characteristics, the temperature of the day of the pour, if it rained or not, all of these things that we don't control, and maybe our models don't really reflect, then you could have much better performance or much worse performance. Instead of having life safety, you can have a total collapse for the same value of target displacement, or you can have a functionally recoverable building or immediate occupant, or a building that can be immediately occupied right after the event, even after reaching that value of drift, right? So what we are going to do in this module is using quoFEM and using OpenSea Stickle implementation to quantify the uncertainty in pushover curves, to really look at how is the range that we can see here of uncertainty around that pushover curve. So first, we're going to look at that, do a pushover curve nominal, understand and kind of look at that. And then the students will have the opportunity to do multiple runs in a forward propagation type of problem and estimate the uncertainty of that pushover curve. So all of that in the next video. Thank you so much.